welcome to two projects. In this video, we are going to explain the project Real-Time Helmetless Detection System for Lift Truck Operators based on improved YOLOv5s. Before diving into the execution, let me give you an overview of the project. So, the Helmetless Detection System for Lift Truck Operators is a safety tool for places like warehouses or factories where lift trucks are used. So these trucks can be risky, so the people driving them should wear helmets like we wear on the bikes, but sometimes they don't. Ensuring that lift truck operators wear helmets is very important for preventing head injuries and fatalities in industrial environments. But relying on traditional methods like manual inspections or periodic checks can be inefficient and prone to errors. And these methods also lack real time monitoring capabilities, which means accidents can happen without being noticed right away. So, by introducing a helmetless detection system, we can revolutionize this process. So, this system automates the monitoring task, allowing for continuous surveillance of operators' helmet usage. Instead of relying on occasional checks, the system continuously scans for violations. So there comes deep learning algorithms. Deep learning algorithms like CNNs, like YOLO, are adept at recognizing objects within images, making them ideal for detecting helmets. By training a model on annotated data, it can identify helmets in various industrial settings. So, this training allows the model to accurately identify helmetless incidents despite lighting, background clutter, or operator position. This system enhances safety measures in industrial environments. So we will be creating helmet detection system using deep learning algorithms in this project. Now we'll look at the workflow. So the dataset used for this project contains images and annotations depicting lift truck operators. Initially, the images from the dataset are read into the system for further processing. Once the images are loaded, various image processing techniques are applied to prepare them for analysis. This includes tasks such as defining classes such as helmet and no helmet, declaring bounding boxes around objects of interest, and converting the image data into a format suitable for further analysis, usually NumPy arrays. So, after this, to enhance the diversity of the dataset and improve the robustness of the models, data augmentation techniques are applied. So these techniques involve making slight modifications to the images, such as rotating, flipping, or scaling them to simulate different viewing conditions or variations in the appearance of lift truck operators in the scene. So we will be training the models on original images from different angles so that the models can generalize well to different conditions or situations. So after these image processing steps, the dataset is divided into two main parts: training data, which is used to teach the computer models or deep learning models how to recognize helmets of lift operators, and testing data, which is used to evaluate how well the models perform on new or unseen images. So after splitting the dataset into train and test sets, pre-trained deep learning models such as variations of YOLO, that is, you only look once, and SSD are loaded into the system. These models have been previously trained on large datasets and have learned to recognize objects including helmets in images. So the pre-trained models are fine-tuned to the specific task of lift truck operator helmet detection using the training data. So this involves adjusting the model's parameters to improve its performance on this particular task. Once the models are trained, they are evaluated using the testing data to assess their performance in accurately detecting helmets of lift truck operators. So, this process helps identify which model is performing well for detection and provides insights into areas for further improvement or optimization. So, this is what happens in this project. Overall, the helmetless detection system for lift truck operators is designed to enhance safety for lift truck operators, managers, and safety personnel. It reminds operators to wear helmets, helps managers enforce safety rules, and allows safety personnel to respond promptly to violations. Using deep learning techniques like CNNs, that is YOLO, it accurately identifies instances where helmets are not worn, contributing to a safer workplace environment. Now we'll see the software and hardware requirements to execute this project. Hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software requirements are application needed is Anaconda, primary language required is Python, front-end framework needed is Flask, back-end framework required is Jupyter Notebook, database needed is SQLite 3, and front-end technologies required are HTML, CSS, JavaScript, and Bootstrap 4. Now we look at the algorithms built. In the base paper, author has proposed YOLOv5s using efficient net backbone, and he compared this proposed model with these other models: SSD, YOLOv5s, YOLOv5s with GhostNet, YOLOv5s with MobileNet v3, and YOLOv8. And he concluded that the proposed YOLOv5s with efficient net has outperformed all other models. For improved performance, we are proposing YOLOv5x6 in this project. So we will be building all these models, the models proposed by the author and the model which we are proposing, and we'll compare their performance using different performance metrics like precision, recall, and MAP scores, and we'll select the best performing one among them. For helmet detection. So now we'll understand about the algorithm which we have proposed, that is YOLOv5x6. First we'll understand about YOLO. So YOLO, that is you only look once, is a computer vision object detection algorithm that quickly identifies objects in images by splitting the input image into a grid and simultaneously predicting bounding boxes and class probabilities. Unlike traditional methods, YOLO processes the image just once, making it extremely fast. It predicts multiple bounding boxes and their associated class probabilities for each grid cell, and then removes redundant detections using non-maximum suppression. This results in a final list of detected objects along with their bounding boxes and probabilities. So these are different architectures in YOLO. So YOLO V5X6 is a variant of the YOLO V5 object detection model designed to strike a balance between accuracy and speed. With along 2.4 million parameters, it offers good precision and recall while maintaining efficient processing speed. Its architecture is optimized to handle 1280 by 1280 input images, making it suitable for real-time object detection tasks. So YOLO V5X6 is chosen for this project due to its ability to provide accurate and fast detection, making it well suited for identifying helmets of lift operators. So its medium-sized architecture and optimized parameters allow for efficient processing of images while maintaining high detection accuracy, aligning perfectly with the project's objective of enhancing helmet detection capabilities in complex environments. So after comparing all these models' performance, we have observed that YOLO V5X6 has outperformed all other models in all the performance metrics. So we have deployed YOLO V5X6 into the Flask web application. Now we will be executing the project in Flask web application. So before that, first we need to open the code folder which contains the project source code files. So this is the code folder and these are the contents I have in the code folder. This is sample folder in which I have images on which will make the detections. This is static folder which consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is YOLO v5 and this is YOLO v8 folders. So I'm opening YOLO v5 folder. So here I have train and valid folders. I'm opening train folder. So we can say I have two subfolders again, images and labels. In images folder, I have different lift truck operators images. And in labels folder, I have annotation files. So the label files or annotation files correspond to an image file in the images folder. So these files provide details about the object's locations and classes within the image. So this annotation file corresponds to this image in the same way. This annotation file corresponds to this image. Similarly, each annotation file corresponds to an image in the images folder. So these label files often follow the YOLO format where each line, so this is the line, this is an other line. So each line represents a detected object. So we can see in this image, there are three objects detected. In the first image, there are three objects detected. So each line specifies the object's class index. The first column is the class index, followed by its bounding box coordinates. These are the bounding box coordinates normalized to the image dimensions. So this is x limit, this is y limit, this is the width, and this is the height. So in the same way, I have class index followed by the bounding box coordinates in other label files also. And each label file corresponds to an image file in the images folder. So on these images and label files, we will be training the YOLO v5 model. Here we can see I have train and validation folders. So train set is for training the models and validation set is for evaluating the models. So in validation folder also I have images and label files. So on these images and label files, we will be evaluating the YOLO v5's performance. And here I have another folder, YOLO v8. So YOLO v5, YOLO v8. So these folders contain same images. So these algorithms are trained with same images, but they are annotated differently. The annotation files, the label files will be changing because each YOLO version requires its own specific type of image annotations for training and testing the models effectively. So having separate folders like this ensures that each YOLO version receives the correct annotations it needs to function properly. That is why we have two separate folders for YOLO v5 and YOLO v8 here. So this is about the dataset. Now coming to app.py file. So this .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the train models. This is Notebook Jupyter source file. So this Jupyter Notebook file contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So it stores information like user signup details. This is about the code folder. Now copy the path of the code folder from the address bar of the file explorer. This is the path. Copy it. Open Anaconda prompt. Use the command cd followed by space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, local host, and port unless configured differently. So this is the local host and this is the port. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I usually prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register ourselves first, fill in all these details and click on register button to sign up. And if we already have account, we can directly log in by clicking on this link. So as I'm already a member, I'm clicking on this link. Here we have to give our credentials, username and password. I'm giving mine and click on login button. So it has redirected us to the detection page. So now we have to upload any industrial lift truck operator's image and the application will detect if the persons in the image are wearing helmet or not. Click on choose file button. So from sample images folder, these are the test cases I have. We'll try uploading the first image. Select the image, click on open. The image has been loaded. Now click on upload button. We can see the application has detected the persons wearing helmet. It has drawn a bounding box around the face, around the helmet, and we can see the label here telling us that the persons are wearing helmet. And beside the label, we can see a probability score telling us the confidence level of the application in labeling these persons as wearing helmet. Click on back, click on choose file. We'll try uploading another image. This time we'll try with this image. Select the image, click on open. Image has been loaded. Now click on upload button. We can see the application has detected the people who are not wearing helmets. It has drawn a bounding box around the detected people. And we can see the label here that is no helmet. Beside the label, we can see a probability score telling us the confidence level of the application in labeling these persons as they are not wearing helmet. Click on back, click on choose file. We'll try with this image. We can see the application has detected the persons wearing helmet. This is the uploaded image and here we can see the application has detected the person who is not wearing helmet. We'll try with this image. We can see the application has detected the persons wearing helmet here and the persons who are not wearing helmet. We can see the probability score beside the label telling us the confidence level of the application, how confident it is in classifying the persons into that particular class, helmet or no helmet. We'll try with this one. We can see the application has detected the persons who are not wearing helmet. We can see the bounding box is drawn. We can see the label that is no helmet and we can see the probability score. We'll try with some more test cases. We'll try with this one. We can see the application has detected the person who is wearing helmet. We'll try with one more image. We'll try with this one. We can see the application has detected the persons who are wearing helmets. So in this way, we have to upload images from the test cases and get the detections if the persons in the image are wearing helmets or not. So we can see the application has detected the person who is not wearing helmet. We can see the bounding box drawn, we can see the label, and we can see the probability score. Click on back. We can also execute the project using images from Google. We'll try that. So I'm searching for lift truck operators working images. So these are the results I've got. So we'll try uploading this image. Download the image. Click on choose file. Select the downloaded image and click on open. The image has been loaded. Now click on upload button. So we can see the application has detected the persons who are not wearing helmet. It has drawn a bounding box and labeled them as not wearing helmet, that is no helmet. And beside the label, we can see the probability scores telling us the confidence level of the application in labeling them as not wearing helmet. Click on back. This time we'll try uploading this image. Download the image. Click on choose file. Select the image. Click on open. Click on upload. We can see the application has detected all the people who are wearing helmet. We can see the bounding boxes drawn around the detected helmets. We can see the label that is helmet, and we can see the probability scores telling us the confidence level of the application in labeling them as wearing helmets. We'll try uploading this image. So it is saying only JPEG or JPG files are allowed. The format is not suitable. We'll try with another image. We'll try with this one. Click on choose file. Select the image, click on open. The image has been loaded. Now click on upload button. We can see the application has detected the people who are not wearing helmets. We can see the bounding box is drawn. We can see the label that is no helmet, and we can see the probability scores. Click on back. We'll try with some more cases. We'll try with this one. We can see it is not suitable format. Click on OK. We'll try with this image. We can see the application has detected the people who are wearing helmet. He is the one wearing helmet, and the application has detected the person who is not wearing helmet. We can see the bounding boxes drawn, and we can see the label, and we can see the probability scores. Click on back. We'll try with one more image. We'll try with this one. Select the image, click on open. So it is saying that it is not in a suitable format. Only JPG files are allowed. We'll try with this one. We can see the application has detected one person wearing helmet. We'll try with this image, one last image. Click on choose file, select the image, click on open. Oh, it is saying only JPG files are allowed, not in a suitable format. We'll try with this image. We can see the application has detected the person who is wearing helmet. We can see the bounding box drawn around the helmet detected. We can see the label and we can see the probability score telling us the confidence level of the application in labeling this person as a helmet wearing person. Click on back. Now we'll look at the graphs. Click on graphs link here. Here we can view all the graphs plotted. This is precision recall graph of YOLO. This is F1 score graph. This is confusion matrix graph. In this graph, these diagonal boxes are the correct classifications and remaining boxes are the misclassifications. And this is precision scores comparison graph, a horizontal bar graph. In this graph, on x-axis, I have precision scores. And on y-axis, I have algorithm names. So these are all the algorithms built. So similarly, this is recall scores comparison graph. And this is MAP scores comparison graph. So we can see YOLOv5s has outperformed all other models in all the performance metrics. So these are the graphs plotted. Now click on sign out. So this helmetless detection system using deep learning actively promotes safety in industrial workplaces by efficiently identifying who is wearing helmets and who isn't. It aims to enforce safety rules, prevent accidents, and ensure a safer environment for everyone involved.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.